Welcome. Today, we're diving into the world of computational complexity. In this video, we will explore how to understand algorithm efficiency. We'll discuss key concepts such as time complexity, which is how execution time grows with input size, and space complexity, which is how memory usage scales with problem size. Let's get started. So, what exactly is computational complexity? It is essentially a measure of the computational resources required by an algorithm, expressed as a function of the input size. This helps us to understand how efficient an algorithm is. We will now discuss some key points. First one is resource analysis. Computational complexity quantifies the time and space requirements of an algorithm. Second one is scalability. It predicts the performance of the algorithm when dealing with large datasets. Let's delve into time complexity. By definition, time complexity is the amount of time an algorithm takes to run as a function of the input size. It's often expressed using big O notation, which looks like this: T of n equals O of f of n. Here, n represents the input size, and f of n describes the growth rate of the algorithm's execution time as the input size increases. Now let's explore some common time complexities you'll encounter. First, O of 1 constant time complexity. Examples include array access and hash lookup. Next is O of log n logarithmic time complexity. Examples include binary search and balance trees. Next, O of n linear time complexity. Examples include array traversal and linear search. Finally, O of n squared quadratic time complexity. Examples include nested loops and bubble sort. Let's illustrate time complexity with an example: the linear search algorithm. Here's the code: def linear underscore search with array and target as inputs. For I in range of length of array, if array of I equals target, then return I. Return -1. The best case for this algorithm is O of 1, while the worst case is O of n. Looking at the complexity analysis, the time complexity of this algorithm is O of n, because the loop executes at most n times, where n is the array length. Let's shift our focus to space complexity. By definition, space complexity is the amount of memory an algorithm uses as a function of the input size. It is important to know the components of space complexity. First is auxiliary space, which refers to the extra memory used by the algorithm, and next is input space, which represents the memory required for storing input data. Let's explore space complexity with an example: the recursive factorial function. Here's the code: def factorial of n. If n is less than or equal to 1, return 1. Return n multiplied by factorial of n minus 1. Note that the call stack grows with n, with each call using O of 1 space. Looking at the space analysis, the space complexity of this algorithm is O of n, because recursive calls create n stack frames in memory. In summary, let's recap the key takeaways from this video. We have time complexity, which measures execution time growth with input size, and space complexity, which measures memory usage growth with input size. Both complexities help us analyze and compare algorithm efficiency for scalable solutions. Understanding these concepts is crucial for designing efficient and effective algorithms. Thanks for watching. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.